All right. So part 2, what was our question? What did we have to hold constant? Let's go to Peter. What was the question for part 2?
How does the acceleration depend on its own mass?
Good. How does acceleration depend on m? All right, Peter, keep it going. What do we have to hold constant in this part of the lab?
The net force and the falling mass.
Couldn't be the mass because we're going to be changing the mass. So I think I go along with what you first said, the net force, right? So F net is the thing that we held constant. Now, do you remember in the lab, how did we actually hold F net constant? What did you do? Go to somebody else on this one. Experimentally, what did you do to keep the net force constant? What was this about? You weren't transferring masses here, were you? Because that wouldn't be holding the net force constant. Trish?
Kept the falling mass constant.
You kept the falling mass constant. You never added to it. Yeah, you just kept it the same. Good. Now, what was that force from that falling mass? I know it was a 50-gram mass, but can you tell me in newtons? How many newtons of weight was that? I want to write that down because that's our constant here. 0.49. Can I write 0.5-ish? Just say it was about 0.5 newtons. Yeah. So it's a pretty small force, but that was the thing that we held constant. Okay. So graphing. You guys made graphs of acceleration versus total mass. And those graphs, or this graph I should say, look different. Okay? In fact, was this graph even linear? No. And some of you made your scales so small you couldn't tell. But most of you did okay, and you put your points up so they occupied most of the graph. This graph looks more like so. It's that type of thing. Now that's definitely a curve, and so I didn't tell you to fit it with a line because that wouldn't make any sense. The question would be, what kind of curve is it? Which we have to talk about a little bit because it may not be obvious here. But before we talk about the type of curve, what's happening generally? How does the acceleration depend on mass? How does this graph inform that? What happens when you increase the mass of the object? What happens to acceleration? It decreases. That's way important. The fact that if you have more mass in the cart, you get less acceleration. Why is that true? Why is it that when you put more mass on something, it accelerates less? What is it about mass that we know that resists acceleration?
Inertia makes it so that it doesn't want to move or change motion, I should say.
That's exactly why. The fact that mass is inertia. And the more stuff you pile onto that, the more mass you pile onto it, the more inertia the cart has, which means the harder it's going to be to accelerate. Remember when you pulled the tablecloth out from underneath the dishes? What was easier? Pulling it out from real dishes or pulling it out from paper dishes? Real dishes, right? Surprisingly, right? The real dishes are easier because what do real dishes have more of? They have more mass, so they have more inertia. So this kind of goes along with that idea that more inertia causes less acceleration. So I think that's probably worth saying here. So star. The acceleration is not directly proportional to mass, right? How is it proportional? It's an inverse. It's inversely proportional to mass. Really important. Forget about the math. Just knowing that is really important. Questions on that? All right, well, let's look at the math now. Because this, what would a math teacher say about this, right? A math teacher might try to fit this curve. And a math teacher might try to fit this curve with this function first. What do you think? You ever plotted something like that in math class? Y is equal to 1 over x? Or y is equal to a constant divided by x? Yeah. Do you know what the name of that shape is when you get it? I mean, by the way, it is the shape. It's called a hyperbola. I don't know if math teachers always say it, but sometimes we would just refer to this shape as a hyperbola. It's not a parabola because in order to be a parabola, I'd have to have a square in here someplace, right? And there isn't. This is just y is equal to 1 over x. So that's called a hyperbola. And the deal with a hyperbola is kind of like this. When you change the x part of it, the y part changes by dividing. So for example, if you double x in this formula, what happens to y? Think about it. If you double x, what would happen to y? It goes down by 1/2. Yeah. If I triple my x, what happens to y? It goes down by 1/3. Doubling this, tripling this, think about this. This is a fraction, right? And that drops down. Now, that gives me this graph, because if this is my original mass right here, then my acceleration would be here. So this point corresponds to a certain mass and a certain acceleration. If I double the mass, I go from here to here, what's happened is that I now have dropped my acceleration to half of what it originally was. If I triple that mass, now I'm down to 1/3 of my original acceleration. This is what a math teacher would look for to verify that this relationship fits that data. If you looked at your data and you did this, you could actually kind of verify that through numbers. I didn't ask you to do that, but the shape that you're getting is basically a hyperbola, and it's consistent with this curve, right? This curve. So this is an inverse proportion. Now, physics, right? Math teachers, they're great and all, but this is physics class, so we want to take this math formula and make it into a physics one. So you tell me now, what am I going to replace y with? A, acceleration, good. Let's go to x. That's going to be mass. So this is going to be 1 over m. And then we have kind of this pesky constant again to deal with. And I could just write the word constant and be like, I don't know. But I had a hypothesis, right? My hypothesis was this. So if you look at my hypothesis, what do you think goes into parentheses there? Compare this formula to that one. How do I make them the same? I'm going to put what in? The net force. And that would work. That actually mathematically would work because, hey, I held that force constant, didn't I? So it's plausible that really if I plug 0.5 newtons in here, maybe that would allow me to generate that curve again. Now I haven't totally proven it, right? It's just plausible. Because I'm saying that, hey, this is a constant and it does match up with this formula, and maybe that would work. And this formula is also like that one. So this is really also supporting the idea that maybe this formula is good, right? But I really want to lock it down. I really want to know for sure. And that's what we'll do when we graph it in the third graph. Before I do that, do you guys have any questions? So are you okay with the logic on this, what we're talking about? What are the two most important things you need to know about stuff up until now? The two most important ideas. Acceleration is directly proportional to what? Directly proportional to force, and it's inversely proportional to mass. Those are the main ideas, the concepts of this, right? The rest of this is kind of filling in some mathematical detail, but it looks like we've got a formula that backs that up so far. We've got A is directly proportional to F, A is inversely proportional to L. Seems to be working. All right, let's do one last way of graphing this, and then I think we'll lock it in. So graph 3, take a look at what you have.